Okay, if you remember in our previous class, we talked about how we can draw influence line for support reaction, shear force, bending moment through the quantitative approach where we apply the unit load to the structure that we have, and we move the location of unit load in order to get the effect on support reaction, shear force, or bending moment. So in the calculation that we had before these, our load was always a unit load, and we said we use a unit load for the sake of simplicity. However, in reality, when your bridge is subjected to real forces, let's say a truck or a car, first of all, the intensity of force is not unit. And second, you may have 2 or 3 point loads that are moving together at the same time. Or even you may have sometimes a uniform load that it is passing over your bridge. For example, if you have a tank, the tank that they use for war, or if you have, let's say, an excavator, and normally the load is considered to be a moving uniform load. So in that condition, you may think that how we can use this influence line that we can draw based on a unit load, whether they can be used still, or we need to do some changes. So this is what we are going to discuss today. And in addition to that, we are going to see how we can draw influence line without these calculations, meaning without using the calculating the support reaction where the load is before and after the locations of interest. So this is what we call it Muller-Breslau or qualitative approach. So this is the second thing that we are going to learn in this class today. But first, I'm going to go through the application of influence line, because right now we know how to draw it, and we are going to see how we can use it. And then after that, we will see how we can draw influence line in a simple way through the qualitative approach. Okay, let's go and see how influence line can be used for calculation of basically support reaction and shear force under moving loads. Let me zoom. Okay, consider you have a structure like the one that you see here, and your beam or your bridges has been subjected to 3-point loads, and the intensity of point loads also are not the same. Like maybe you have 10 ton, 15, and 15 as 3-point loads that have been applied to your bridges. And right now, you're interested to know under these 3-point loads, how much is the support reaction in the left side, and how much is the support reaction in the right side? Or how much is the bending moment, for example, in the middle of the span, when these moving loads are passing over your bridge? Okay, so that's what we want to do. Okay, for point loads, in order to basically calculate the support reaction under the point loads, the only thing that you need to do is to multiply the intensity of point loads to the height of your influence line that correspond to the same location. For example, here we have a 10-ton force applied 3 meters after the left span. So this is the influence line for the basically support reaction in the left side. It starts from 1 and it goes to the 0 when it reaches the right side. So we know this one how to draw it from our previous class. So right now, if you have a 10-ton, 15-ton, and another 15-ton applied to this beam, and you want to know how much is the support reaction at point L on the left support reaction, you just need to multiply the value of this point load to the height of your influence line. So it's going to be 10 multiplied by 0.8, 15 multiplied by 0.4, and another 15 multiplied by 0.1. These 0.1, 0.4, and 0.8 are the height of the influence line at the location that the point loads have been applied to the bridge. So if you do this calculation and you sum it up, it is going to give you how much is the support reaction at point L on the left side when these 3-point loads have been applied to your bridge, like the one that you can see here. From the first load we have 10 multiplied by 0.8, we get 8 ton. From the second load, we have 15 multiplied by 0.4, 15 multiplied by 0.4, and from the third load, we have 15 multiplied by 0.1. So if you sum up all 8 plus 6 plus 1.5, you get 15.5. That means the support reaction at the left side equals to 15.5 when your moving load are in these positions. One of them is here, one of them is here, and one of them is here. So if this moving load is moving again, let's say 15 ton reaches to point R, and this one comes here, and this one comes here, doesn't matter. Again, you need to multiply their intensity to the relative height of your influence line. Of course, if you want to know what case is the worst case scenario for your bridge, you need to examine different conditions. For example, you may say that, okay, let's start first put this 15 ton here and another one here to see it gives us a larger value or not. This is something that we are going to discuss later. Of course, for the design, you're looking into the worst case scenario and you need to find it by trial and error. Okay, so this was very easy. So if you have a point load, you just multiply the point load to the height of your influence line. Although you have designed or defined this influence line for a unit load, but it can be still used for any type of point load with any intensity. As I said, you just need to multiply the value of point load to the height of your influence line and then sum it up. If you had only one point load, you didn't have these two, you just multiply 10 to 0.8, and this is going to be the reaction in the left side. If you had only this 15 ton without these two, you just multiply this 15 ton to 0.4. If you had one more point load, then you can just add that point load and multiply to the height. In other words, how many point loads you have on the bridge doesn't matter. You just multiply the intensity of your point load to the height of your influence line and sum it up. That is going to give you the value of your influence line due to that point load. For bending moment, also is the same. If you want to know how much is the maximum bending moment in the middle of the span, first you draw the influence line for the middle of the span, which is going to look like this one. Now you have the influence line for the middle of the span for bending moment. You know that you have drawn this one for a unit load. If you want to know how much is the bending moment due to this point load that is moving, then you just need to multiply their intensity to the height of your influence line. So for this one, it's going to be 10 multiplied by 1.5, 15 multiplied by 3, and 15 multiplied by 0.75. That is going to give you the value of the bending moment in the middle of the span due to these 3-point load, as has been done here. 10 multiplied by 1.5, 1.5. Again, 15 multiplied by 3, 15 multiplied by 3, and 15 multiplied by 0.7, 0.75. So you just sum up all. This 71.25 is the bending moment in the middle of the span due to these point loads. Of course, again, here you can just say, is this the worst case scenario for the bridge, or we may have even larger than that? This is the time that you need to examine different cases. For example, you can put this 15 ton in the middle, and this 15 ton, of course, is 4.5 meters after that, comes here, and this 10 is going to shift to this side. And calculate to see you get a larger value or not. So this is basically how we can use influence line in order to calculate the value of support reaction and bending moment or even shear force when we have different type of point loads on our structure. So it was very easy. We just need to multiply the intensity of point load to the height of influence line. The moment that you get the influence line, the job will be after that multiplication of the intensity of point load. Another issue is that right now we have only point load. What if we had a uniform load on our structure? For example, the beam itself here has its own self-weight that is working as a uniform load. Or you, as I said, you may have a tank or you may have an excavator or any type of load that can pass over your bridge and consider to be a uniform load. How we can do the calculation for a uniform load? Okay, if you had a uniform load, the calculation is a little bit different from point load. In the uniform load, you need to multiply the intensity of your uniform load to the area of your influence line. For example, for the previous beam, if we have a uniform load, let's say with the intensity of 3 ton per meter, passing over the bridge, or it is all over the bridge, then you need to calculate how much is the area of your influence line under the uniform load. In this case, uniform load is all over the span. So if it is all over the span, you need to calculate the whole area of your influence line because the uniform load is covering the whole span here. So you need to calculate the area. The area is 15 multiplied by 1 divided by 2 because this one is a triangle. So the moment you calculate the area, then you just need to multiply it to the intensity of your uniform load, like the one that you see here. 15 multiplied by 1 multiplied by 0.5, and then multiplied to the intensity of the uniform load. This gives you 22.5. That means if this uniform load is on the beam, the support reaction in the left side equals to 22.5. Okay. For bending moment also is the same. If the uniform load is all over the span, you calculate the whole area of your influence line for bending moment. So the area is just two basically triangle. You calculate the area and then multiply it to that 15. This is what we have done. You have two triangle, or you can just consider it to be one large triangle. The height is 3.75, the length is 15. So 15 multiplied by 3.75 multiplied by 0.5 gives you the area. And then after that, you multiply it to 3 because the intensity of uniform load is 3. So you get the bending moment in the middle of the span to this uniform load. Another case is the time that your uniform load doesn't cover the whole span. It might be covering only half of the span or 1/3 of the span. So your job is just to calculate the area of influence line under the uniform load. Since right now the uniform load is in the first half of the span, so we just need to calculate the area of the first half of the span for the influence line, meaning our load is from here to here. This is the center line. So we just need to calculate the area of this trapezoid shape that we have here. This trapezoid shape, let me show it to you. Okay, this one. Need to just calculate the area of this trapezoid because the uniform load is only here. So the area corresponding to this is going to be this area. For the bending moment also, again, only this area is going to be calculated and multiple to the intensity of this point load, this uniform load. If the intensity is 3 multiplied by this A gives you the intensity of support reaction in the left side. And if you want to know how much is the bending moment, it's going to be 3 multiplied by this area. It gives you the intensity of bending moment in the middle of the span. So if your influence line, let's say, had positive and negative, then when you calculate the area, you should consider the positive and negative sign as well. For example, if you want to calculate the intensity of influence line for shear force, for example, in the middle of the span. So the shear force in the middle of the span has negative and positive sign. So if your load is all over the span, this area should be multiplied with its sign plus this area. So it may be reducing each other, it becomes a smaller value and then multiple to the intensity. So if your influence line had positive and negative, and your uniform load was all over the span, the area is coming with its positive and negative sign. This side is positive plus this side is negative, and then sum it up. Similarly, if you had a point load, 1 point load in the positive sign and 1 point load in the negative sign, then again, you need to multiply it considering the sign of your influence line. If this height is positive, so the point load multiplied by positive plus this point load multiplied by the negative height, and then sum it up. So positive and negative should be considered exactly inside your calculation. You cannot consider it always positive or always negative. You need to look into your influence line and look into the location of your point load and uniform load. Those that fall into the positive area, you consider it positive. Those that fall into the negative area, you consider it negative. And then at the end, you sum them up. Okay, any question until now? Any question? Everything is clear? Okay. Let's go and see one example. We have a beam here. You can see this cantilever as a cantilever part. And then our intention is first to draw the influence line for shear force, the point D, which is 3 meters after point A. And then we want also to draw influence line for bending moment at point D, and which is 3 meters after point A. Then after that, we are going to calculate the maximum shear force and maximum bending moment due to the load that has given to us. One of the loads is a uniformly distributed dead load with the intensity of 1 ton. So we have a uniformly distributed all over of the span. Intensity is 1 ton. And due to that, we want to know how much is the shear force at point D, maximum shear force, and how much is the maximum bending moment at point D. In addition to that uniform load, we have point load with the intensity of 1 ton, and another uniform load with the intensity of 5 ton. So we have 2 uniform loads. One is all over the span, intensity is 1. Another one is a live load that can move. When we say dead load, that means, or self-weight, that means that one doesn't move. It's just a weight that covers the whole span without having any movement. But normally live loads are the one that can move, and so we should consider the worst case scenario for them. So we have 3 types of load applied to these basically bridge or beam. 2 is uniform load. One of them is the dead load that doesn't move all over the span, 1 ton. Another one is 5 ton that can move, and another one is a point load with intensity of 10 that it can move also. So first thing first that we need to do is to draw the influence lines based on a point load of intensity of 1, as we learned before this. So this is something that you have learned. I don't go through it. And the result is going to be similar to the one that you can see here. For shear force, you can first draw the influence line for support reactions, and then based on that, you can draw the influence line for shear force and bending moment. This is what we learned, right? So you can draw first the influence line for support reaction at point A, and then after that, you can cut your beam before point T and after point T, and then write down sigma phi equals to 0, and then get the value of shear influence line and bending moment. If you do that, this is going to be the basically shape of influence line for point D. And then the bending moment influence line at point D is going to look like this one. So you can see we have positive areas, we have negative areas, positive areas. It doesn't matter which one you consider positive, which one you consider negative. Normally the one is above the line is positive, the one that comes below the line negative. But that doesn't change anything. You can consider it vice versa. As long as you are consistent, meaning all above should be positive or all above the line should be negative. Okay, so we need to calculate each one of these areas because you have uniform load, and we learned that if you want to calculate the support reaction or shear force or bending moment diagram's value, and you have a uniform load, it should be multiple to the areas. So that's what we have done here. Let me enlarge it. Okay, so you can see here we have calculated the area of this triangle, the area of a small triangle, and area of a large triangle. And similarly for influence line of bending moment, we have calculated this area, and this area. So each one of these areas have been calculated, and later on, in order to calculate the total reaction, we need to multiply them to the forces given to us, which has been done in the next page. Okay, first we go, we do the calculation for the maximum shear force, and then we have 3 types of load, as I said. One of them is uniform dead load that doesn't move, so it is all over our span. Another one is a uniform live load with the intensity of 5 ton. This 5 ton can pass all over the span, so it is moving, basically moving time. And then we have also one 10-ton live load point force that also can move all over our span. So for the dead load, since it doesn't moving, basically it's always there, and we don't need to be too much basically worry about the location, because the location is always constant because it is dead load, it doesn't move. So since it is a dead load, we just need to calculate the area of our shear force influence line and then multiply it to the value of intensity of the dead load, which is 1 ton. So that's what we have done. If we go back to the previous slide, you can see we have 3 areas, 1.25, negative 0.45, and positive 2.45. So this area plus this area plus this area is the total area under the uniform load, which is the dead load for us. So 1, which is the dead load, uniformly distributed over the span all over, should be multiplied to the summation of these 3 areas. So this is what we have done. Sorry, okay. 1.25, you see the negative sign is already there, negative 0.45 plus 2.45. So summation of these areas multiplied by 1. Why we consider all the areas? Because the uniform load is a dead load and it is covering all over the span. So all the areas should be summed up. So the result is 3.25. That means the shear force at point D due to the only this dead load, which is uniformly distributed all over the span, is 3.25. But we have 2 more loads that we need to calculate. Since we are looking into the maximum, so for the other 2 load case, we should find the worst case scenario. The worst case scenario is the case that makes the total force larger, okay? So far we have 3.25 coming from uniform dead load, and we need to see from the live load how we can make this VD maximum, okay? So since this 3.25 is a positive sign, we need to find the location that the shear force is going to be positive. This way we can add to this one. If our shear force become negative from these point loads and uniform load that are moving, then it's going to decrease this value. So if you go back to our previous slide, you can see we have 2 areas which are positive and 1 area which is negative. So our basically live load with the intensity of 5 ton, it can be all over the span, or it can be partially in each one of these span that has positive sign because it is live load, okay? So the worst case, in order to make all the results positive, is when this 5 ton, this 5 ton uniform load, it is only on the positive side of the graph, only on the positive side. This way, if you multiply them to the areas, you get a positive value, and then we can sum it up with the value that we got from the first point uniform load, which was a positive value. So that's why we did not put the uniform load here, meaning if we have a condition in which this 5 ton can only stand on the positive side, it is making the value of shear force more than the time that it is all over the span. Because if we have also 5 ton here in the middle, the negative sign of the area is going to reduce the value. So that's why, as you can see in the next slide, we have only considered the 2 areas that are positive. So that's why we have only 1.25 plus 2.45. We didn't put this one here. Why we can do that? Because this is a live load and we can adjust the location to be the worst case scenario. So we multiply it to the 5, which is the intensity, and it gives us 18.5. 18.5 is the maximum shear force for VD when we have this 5 ton force in the positive areas. Similarly, we need to look into the point load of 10 ton to see how we can make, again, a large value with positive sign. So if you go back again to our influence line, you can see we have 0.5 here and 0.7 here. So between these two, because for point load, we said we just need to multiply it to the height of the graph. So the one that gives us the largest height is going to make the shear force larger. So from the positive one, we have 0.5 and 0.7. Of course, 0.7 is larger than 0.5. So if you multiply this 10 ton, meaning if the point load is coming to the location that is after point D a little bit, this is going to give us a larger value compared to the time it is here, 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 or any other place. So since we are looking to the maximum VD, we are going to put our point load also to the case that gives us the worst case scenario. So if I want to show you what is the worst case scenario that can happen for this breach, is the time that we have these 5-ton forces in the positive area, and then we have also the uniform dead load, which has been applied to it with the intensity of 1 all over the span. So this is going to be the condition that gives us the worst case scenario, meaning the largest VD is the time that the forces are arranged along the span according to this diagram. As I said, the force can be in any condition, maybe here, but that doesn't make the VD to be maximum. So for 10, also we need to calculate similarly. 10 multiplied by 0.7 is going to give us the value of shear force due to the point load. So we get 7 tons from here, 18.5 from the moving load, uniform load, and 3.25 from the steady dead load. So if you sum up these three, you get 28.75. So this is the value of VD, which is a positive sign, okay, which is positive sign. The value of VD also can be calculated for the negative sign. And the calculation is going to be such that our result is giving us always a negative value. And we can just see how much is the VD mean, or the VD that has negative sign. So the calculation is going to be similar to the previous one. Again, the dead load is, since it is all over the span, we can't do anything about it. We just need to sum up all the areas and put it there, 3.25, similar to the one that we did up here. But for the other two live load that we have, we can put them in the locations that gives us only the negative values. So if you go back to the graph again, you can see our negative area is only this area. Therefore, if you want to calculate a negative shear force, which is maximum, our 5-ton force should come here. And of course, the point load of 10 ton also should come here. That gives us this negative 0.3. So this is going to be the case that gives us the largest, basically, negative sign shear force. We have 1-ton force all over the span, which is a dead load, doesn't move. 5-ton moving load only applied to span AD, and the 10-ton point load that has been applied a little bit on point D with negative 0.3. So if you sum up all these values, this is the time that you can get negative 0.2. 3.25 come from the dead load. 5 multiplied by negative 4.5, this is the area of AD, is giving to you negative 2.525. And then for point load, you get 10 multiplied by negative 0.3, you get negative 3, and totally is going to be negative 2. So you can see, if you compare the value of 28.75 and negative 2, the shear force is positive sign is the maximum value. And this is going to be used for the design if it is needed, okay? So from this example, you can realize that in order to calculate the worst case scenario, you need to examine different conditions. And this is just by looking into the areas that gives you the largest area and to the height that gives you the largest height. And then you will put your load in that condition to get the worst case scenario. Okay, let's go and do the same calculation, this time for bending moment. So you can see in bending moment, we have two areas. One is negative side and one is positive. And now our interest is to calculate how much is the maximum MD, maximum positive and maximum negative. Okay, this is what we have for MD. Let me enlarge it. Okay, in order to calculate maximum MD positive, again, we have these three loads. We separate the calculation for each load. For uniform dead load, of course, it is all over the span, so we just need to calculate the area and multiply it to the intensity of our dead load, which is 1. So area is two triangles. One of them is 10.5, one of them is negative 8.5, 8.75. So totally the area multiplied by 1 gives us positive 1.75. So this bending moment is due to the uniform load. And now we have two live load. Again, we need to find the condition that makes it maximum positive. So since we have two areas, one is negative, one is positive, of course, this live load should be placed on the area that has a positive sign. This way it's going to be added to this positive 1.75. So that's why the intensity of 5 multiplied by 10.7, 10.5 gives us 52.5. So this is for the uniform load. For point load, again, we need to find on our influence line diagram what is the largest height that can give us the largest value of bending moment. So if you go back, you can see we have negative 3.5 and we have positive 2.5. That means if our load is here, the point load, it's going to give us a larger value. So if I want to draw again here for you, what is the worst case scenario for the positive bending moment is the time that the point load stands here, and then the uniform load of intensity of 5, the live load, is here, and then we have our also dead load all over the span. So in this case, basically, the bending moment gets the maximum value with positive sign. 5 multiplied by 10.5, 10 multiplied by 2.1, and 1 multiplied by 10.5 minus 3.5. So this is going to be the worst case scenario for positive bending moment. So that's what we have done, and you can see in our next slide. Okay, so this is the calculation. This is the calculation. 1 multiplied by that, 5 multiplied by this, and 10 multiplied by 2.5. So totally you sum it up, you get 75.25. This is the maximum bending moment with positive sign. If you want to calculate the maximum bending moment with negative sign, we need to go through the same calculation. First, we have the uniform dead load that doesn't move. So similar to the first case, it's going to be the same value because the dead load cannot move. So you just multiply it to the area or the whole area of the bending moment influence line. And then for the live one, again, we need to find the worst case that gives us maximum negative this time. Before this, we were looking to maximum positive. Here, we're looking to maximum negative. So if you go back again to the influence line, you can see the worst case for maximum negative bending moment is the time that our moving live load with intensity of 5, it's in this area because it is negative. And then our point load with the intensity of 10 is exactly in the beginning of the span because this is the maximum value that we have for negative. And then, of course, we have also up there the dead load, which is all over the span and should be multiplied to the whole area. So this is going to give us the maximum negative bending moment. 1 multiplied by 10.5 plus negative 3.5, 5 multiplied by negative, 1 multiplied by 10.5 plus 8.7 negative sign. Then this 5 multiplied by this area, which is negative 8.75, and 10 multiplied by this height, which is negative 3.5. So that's what we have done. Okay, so let's go to the next page. Okay, you get from the dead load 1.75, then negative 43.75 from the uniform live load, and from the point load, also you get negative 35. So if you sum it up, you get negative 77, which is larger than 75.25. Meaning, if you want to design this beam, you need to use this bending moment in order to calculate the size of your beam, because this bending moment is larger than this bending moment. Okay, so this is how you're going to do the calculation for maximum bending moment and maximum shear force. And as I said, it is based on trial and error. You need to look into your graph and see in what condition basically you can get the maximum values based on the areas and the height of your influence line. Okay, if you have any question until now, please ask. Otherwise, we can continue with our next topic. Any questions so far? So you know how to calculate the maximum value for shear force and maximum value for bending moment? Any question? Okay, if you don't ask question, as I said, I'm going to ask question.
Doctor,
Yes,
question. So,
yes, please ask.
if in the test that we will do, will it be the question will ask about the maximum positive or maximum negative, or we have to calculate both of the MD maximal positive or maximal negative?
Normally, we say to you, calculate the maximum. Okay, that maximum meaning maximum negative or maximum positive. You need to calculate both and see which one is giving you the worst case. Normally, we don't say calculate the maximum positive, maximum negative. We just say calculate the maximum. So you need to calculate both of them and see which one is the worst case.
Okay, thank you, Doctor.
Okay. Okay, so right now I give you one question, and after a few minutes, I'm going to ask you to answer. Okay, for the same graph, for the same influence line, assume that we have 2-point loads. The distance between the 2-point loads is 3 meters. Is 3 meters. One of them is 20 and one of them is 10. Okay, so I want you to calculate how much is VD max only due to this point load. If this point load is passing over the bridge 10, 20, it's moving from left side to right side. Distance of these two loads is always 3 meters. It is like a car that has 2 wheels. So this car is passing over our bridge. The first wheel is 20, the second wheel is 10. So it's passing all over this bridge, and we want to know how much is VD max. VD max only due to this live load. I don't want the other loads, just omit these loads. Consider that we have only this load, 20 and 10, and we want to see how much is VD max. So you have 5 minutes to calculate this. Then I will ask one of you to answer. Okay, so let's see who is volunteer to answer the question. Anyone wants to answer?
So just one question before. So this is a live load, right?
Yes.
Okay, and we can have more than one live load at this span. So we can have this
Yes,
one
this
twice.
is 2-point load that both of them are moving, but the distance between these 2-point live load doesn't change. It is 3 meters, like a car. As you can see here, there is a car passing over the bridge and it has 2 wheels. Each wheel has its own weight. One of them is 20 ton, another one is 10 ton.
Yeah, but can we have it like twice? Like one time between CA and another time between DB? 2 times at the same time?
I don't understand what you mean.
So it's live load, right? So can we have like 2 live loads at the same time? The same live load,
Yes.
one time at
Yes.
CA and one time at DB? Because if that's possible, then that's the worst case scenario. At the positive.
What do you mean by 2 live load? Meaning another live load applied to the bridge at the same time that these 2 are there?
Yes, but it's the same live load. So that's the worst
Yes,
case
it can be
scenario.
2 bridges, it can be 2 cars passing over the bridge, it can be another 2 live load moving. But in this question that I gave to you, it is only 1 car passing over the bridge. It might be 2, 3 cars, meaning it can be 2 of these live load at the same time are moving.
So in this case, the worst case scenario will be between CA and DB only.
CA and DB?
Yes.
Yeah, if you're looking to the positive, yes, but you need to kind of find out in what case, meaning this car, if the car stopped in what condition or what position, the value of ED is going to be maximum. We are looking into the maximum, not into the area. We need to say exactly if this car is stopped here at point D or at point C or at point A, the value of ED is maximum. We need to look into that.
Solve this. Yeah. So I need to solve this like 5 times. Each 3 meters. At each 3 meters.
No, it's not like that. You need, by looking at the maximum values, you can directly understand which location is the worst case scenario. I will tell you how you can do that.
Okay.
Okay, anyone can answer the question? Okay, let's go and check one by one. Alison, yes. Please open your mic and let me know whether you can answer the question or not.
Yes, doctor.
Okay, so what is the answer?
What I calculated is 111.
111?
Yeah.
111, you mean?
Sorry?
You mean the maximum VD is 111?
Yes, VD max.
Oh, okay, so in that case, where is the location of our point load?
Location of the point load I put at D.
Okay, this 10 go at point D, huh?
Oh, hell no.
Okay, so how did you calculate 111?
I use
So if point is 10 is at point D, let's say this is the case that you're talking about. Okay, the other one is should come here 3 meters after that. So this is 20, this is 10. So we need to know 3 meters after this point, how much is the height of this graph? So if this one is 0.7, 3 meters after that, you can easily calculate. This one, assume it is X, and from here
yes.
to here, it's going to be 4 meters, because this one is 3 meters already, right?
Yes.
So you can say that X over 0.7 equals to 4 over 7. So from here, you can easily calculate, and X becomes 0.4, right?
Yes.
Okay. My mistake. Sorry. So this is our point load. 10, 20. Distance is 3 meters. Here is 0.4. So right now, if you want to calculate the worst case scenario, you should multiply 10 to the height, right? 10 multiplied by 0.7 plus 20 multiplied by its height, 0.4. Okay, how much is this one?
15.
This is 7. This is 8. So how come you calculate 111?
I think I done the calculation wrongly at first.
Okay. So this is one case. You may just say that, okay, why not we put our force to be in this location, 10 and 20. And the distance is 3 meters. Because this is live load, you can move to any place. And then you can calculate the area, the height here. So if you do that, here you get 10 multiplied by 0.5 plus 20 multiplied by, so here if this one is x over 0.5 equals to 2 over 5. So it's going to be 0.2, if I'm mistaken. X over 0.5 equals to, this one is 2 over 5. So it's going to be 0.2, this one. So it's going to be 20 multiplied 0.2. So if you calculate this one, you get 5 plus 4, you get 9. So this one is much larger. So you see, two cases are basically available. One is when the point load comes to point D. One of the forces is standing here and one of the forces stands here. In that case, the value will become 15. Another case when our load is coming to this location. 10 force is here, another 20 comes here. So 10 multiplied by this height become 5, 20 multiplied by this height become 4, totally become 9. Of course, you may just say, why not you put the load before the bridge? You can examine any different cases that is possible, but at the end of the day, the worst case is going to be this case, which is 15 ton. And this is going to be the VD positive, VD positive. So the answer is 15, and the case that gives us the worst condition is the condition in which the car stops at point D. The last wheel is at point D, and the front wheel is going to be 3 meters after that, and gives us this value. Any question? Everyone understood how we do the calculation? If you have a question, please ask right now.
Doctor,
Yes.
I want to ask if for this scenario, can I invert the position of 20 and 10 so that like I use 20 times 0.7 and then 10
No. Because when we give you the value of the point load, we are referring to one specific car. Meaning this is a car that is passing over the bridge. One of them is 10 ton, another one is 20. So if you want to change the location of these two, that means you want to change the location of the tire of this car. That is not possible.
Okay.
Okay, this load represents this car. So 10 and 20 are part of the load of this car. You cannot change them. Although both of them are live load, but when we give you a distance of 3 meters, that means it represents a car similar to the one that you see here. Unless you have one unit point load 10 and another one point load 20, that they are not connected to each other. Maybe this one is a motorbike, this one is another motorbike, for example, passing over the bridge. So in that case, each one of these two can stand in one specific location. Both of them can come in the same location, or they can separate from each other. So in that condition, yes, you can put both of them here, 20 here, 10 here, and put 10 multiplied by 0.7, 20 multiplied by 0.7, you get a larger value. But if it is a car similar to the one that passed over the bridge and the distance between the load is fixed, then you cannot change the location of this point load.
But I mean, when I invert that, it is the distance between 10 and 20 is still 3 meters, so it's not possible also.
Oh, meaning 20 come here and 10 here?
Oh, no. It means 20 at the right direction, but 10 at the right side of 20.
So you want to make it like this, you mean 20 here and 10 here?
Yeah.
You mean? No, this is not possible. Because as I said, when we give you a point load with a distance of 3 meters, whatever it is given to you, it cannot be changed. Meaning you cannot shift this one back, this one front. No. These are constant in the location, and the value is also constant. Only they move. To the right or to the left?
Oh, okay, okay. Thank you, doctor.
Okay. Any other question? Any other question? Everyone understood? Or you want me to ask another question? Okay, so we ask another question. For the same load that we had, meaning this is 10 and 20 with a distance of 3 meters. Calculate what is M negative max. How much is the M negative max? So you have, again, 5 minutes. Okay, so who can answer the question? Anyone volunteer? Anyone volunteer?
Is it?
Yes.
Is it just minus minus
much?
3? Minus 3?
3?
Minus 3.
No, I don't think so. Anyone else? Anyone else wants to give it a try? Okay, Noor Afiqa. Noor Afiqa. Can you open your mic? Noor Afiqa, are you in the class?
Yes.
Okay, what do you think about the answer? First, let's see where is the location that gives us the maximum negative bending moment.
I think it would be from C.
20 ton should stay at that location. Is 20. Should be at C or at A?
I mean,
or 10 go to C.
10 go to C.
Okay, 10 go to C. And then 20 should come, of course, 20 meters, 3 meters after that.
Yes.
So this is going to be the worst case scenario. So if we calculate this one is X. So we are going to see X over 3.5. Oh, sorry, X over 3.5 equals to, okay, 3 is going to be 5, is going to be 2 over 5. So from here, X is how much? 0.5, 1.4, huh?
Yes.
So X is 1.4. Okay. So if you want to calculate M max, is 10 multiplied by negative 3.5 plus 20 multiplied by negative 1.4. How much is this one?
Negative 63.
Negative 63. So you think this is the worst case scenario?
Yeah.
Okay, thanks. Anyone else? Do you think this is the worst case scenario? Anyone has any other idea? Actually, this can be one of the options that we can examine, but there is another option. And that's the option, the second option is the time that the car is only having its first tire on the bridge, meaning the condition is like this one. This is one of the tires, this is another tire. So this is our car. It just came to the bridge and the first tire reaches to the beginning of our cantilever. Okay, so in that case, we have only this 20 because 10 is still not in the graph. So we have 20 multiplied by negative 3.5. How much is this value? Negative 70, right? So you can see compared to this value, negative 70 is larger. So therefore, the worst case scenario is the time that only one of the point load is reaching to the bridge. So that's why you need to examine all possible cases and make sure that you get the worst case scenario for your bending moment. Often the students make such a mistake in the exam as well. So this case is one of the cases that can give us the value, negative something, but the worst than this is the time that only one of the tire pass over the bridge and reach to the bridge basically. Any question? Any question? Everyone understood what we are doing here? Okay, so it seems to be clear for everyone. Okay, inside your basically inside your notes, I have put something also there for you. This technique is only applicable for simply supported bridge. When you have only one span. If you have one span and then you have multiple point loads, like this car that passed over the bridge, it has 3 point load. You want to calculate the worst case scenario, or let's say for a bending moment, for example. So you can draw the bending moment influence line easily. It looks like this color, the black color. So this is the graph of bending moment influence line for the mid of the span. So if you want to know under this 3 point load, where is the basically location of the point load that gives you the worst case scenario, first you need to calculate the resultant force. The resultant force can be easily calculated, meaning you just need to calculate the summation of all force, 10 plus 4 plus 2. For example, in this case, it becomes 16. 10 plus, I think one of them is, there has been some mistake here in the calculation because this is 10 plus 4. Oh, yes, correct. 10 plus 4 plus 2 is 16. So the resultant force, meaning summation of this force, becomes 16. And if you want to find the location of that resultant force, you just need to multiply each one of them to the distance from the first load. So 2 multiplied by 6, 4 multiplied by 4, plus 10 multiplied by 0 equals to R multiplied by this X. So from there, you can calculate the location of that resultant force. And then when you got the location and intensity of that resultant force, in order to calculate the worst case scenario, you can put it between this force and the center line. So place the series of point load at the location where the center of the beam falls in the middle of the resultant force and the maximum point load. So here the maximum point load is 10, our resultant force is 16. So if the center line is exactly between these two, this is the condition that you get the maximum bending moment for this simply supported beam. So this is only applicable to simply supported beam in order to calculate the worst case scenario, but you can just do trial and error like the one that we did, meaning you just see 10 multiplied by this, 4 multiplied by this, 2 multiplied by this, see which one gives you the worst case scenario by moving. And this technique cannot be applied for continuous beam. It is not working there. It was just one idea of how we can calculate the worst case scenario when the number of point loads are more than 2. Okay, so this is another example for the calculation of worst case scenario. Again, you have 2 point load. You can calculate the resultant force, and then you can put it in the middle. This is just one example similar to the previous one. It's not that much difficult to understand. You can do the self-study. Here, I just wanted to highlight that normally when it comes to the design of real bridges, what we do is we get the influence line for different locations. For example, you want to design this bridge under the moving load. So you can calculate the influence line for any of these locations, point A, B, C, D, and one of these locations can give you one value, the other location can give you the different value. But what we need is the maximum of these 3 or 4 locations for the design. So this is the time that we can draw on a spectrum, basically, meaning from each case, we can see how much is the maximum that we get, and then we can connect them to each other for the positive sign, and we can connect them to each other for the maximum negative sign. So the graph that is obtained basically is a spectrum for the whole span, meaning if a point load is moving all over the structure from here to here, you can see how the variation of the bending moment or shear force or support reaction can be for every other location of your span. So this is something that normally is used in the consultant company for their design. But in the exam and test, normally we don't ask you to draw something like this because it's not within the scope of your subject. I just put it here if you are interested to know more, you can read it for your own good. So it is not something related to the final exam or test. Okay, so far, I think we can go to some rest, and then we can come back with the second part of our discussion, which is going to be the qualitative influence line. So if so far you don't have any question, we can have 15 minutes of rest. We can come back at 12, 20, 12, 15, 12, 15 right now, 12:30. We can come back at 12:30 and continue with derivation of influence line through the Muller-Berslov or qualitative influence line. Any question? Okay then, so see you at 12:30.